So welcome back, everybody. Today, in the first lecture, we are going to wrap up the calculation of the energy of the homogeneous electron gas in 3 dimensions. And one of the motivations has been to show you how you can, for a specific system, find analytical expressions for the energies. And in addition, this system has served as a kind of entry point for studies of metals in condensed matter physics, semiconductors, and many other things. So it's a model which has been extremely successful in giving a first qualitative, quasi-quantitative description of many important systems in condensed matter physics and material science. And if you are a kind of many-body physics aficionado, then these calculations of the homogeneous electron gas are very useful because it serves as a test bed for many-body physics. And furthermore, the system can be modified to study neutron stars and infinite nuclear matter, where you can have either just neutrons, which is the first approximation to a system like a neutron star, and then you can add tiny fractions of protons, and you can look at matter in chemical and charge equilibrium, which is what one expects to have in the interior of a neutron star. So the whole setup, this kind of infinite systems, are systems which are extremely useful to study. But for us, it serves also as the entry point to a widely popular many-body method, which is called density functional theory. And Kohn, who was one of the people who developed the theory, was awarded the Nobel Prize in chemistry for computational quantum chemistry in '98. So density functional theory, if you guys end up, let's say, discussing with people from condensed matter physics, material science, but also in quantum chemistry, atomic and molecular physics, this is the kind of state-of-the-art many-body method, which allows you to study systems with tens of thousands of electrons. Then this serves also as a stepping point towards larger systems where you can use a microscopic quantum mechanical calculation to define an effective potential, which is then used in molecular dynamics calculations. And some of you may have encountered that, where you freeze out the quantum mechanical degrees of freedom and construct an effective classical potential which acts between atoms or molecules and ions in solids and materials. It's used in DNA modeling. It's used in chemical reactions and many other fields. And that means that you end up solving Newton type of equations where you have frozen out all the quantum mechanics and you have just kinetic energy plus some potential which these objects move in. And in that case, you can actually deal with systems of billions of particles or even more. And you can study phase transitions, you can study properties of materials when you don't need the detailed quantum mechanical information. So density functional theory provides us with a stepping stone with mathematically sound approximations towards a further reduction of degrees of freedom. So there is a huge landscape of approximations where you can link mathematically different methods in a more stringent way. Instead of just saying in an ad hoc way, I just fit a potential, and I hope that this does a good job in reproducing experiment. So density functional theory is actually a theory which instead of varying the single particle wave functions as we have done now, we vary the density of the system. So I'm going to define that a little bit later here. But the homogeneous electron gas has served as actually a starting point for dealing with density functional theory, because at the end, even if density functional theory is an exact theory, you need a practical calculational scheme. And that practical calculational scheme is called a Kohn-Sham scheme, which means that you replace this density of the ground state in terms of a single Slater determinant and where you end up with optimizing much of the same type of equation as you do in Hartree-Fock theory. So the practical recipe is called Kohn-Sham theory, which we will discuss a little bit more tomorrow. But today we are going to look at the basic theorems of density functional theory. So the thing I want to do first, however, is just to quickly remind you of some of the things we did last week. And then I'm going to switch to the whiteboard and do the final calculation, because there are some mathematical tricks, which, well, I like them. It depends on you guys, whether you like it or not, but I am pretty fond of running calculations of integrals. So when I was an undergraduate student, I simply loved solving integrals. That was one of my favorite spare time activities. Okay, so if we just look at what we have in the slides here, just a quick reminder of what we have. And today, as you also saw from the email, from 1 o'clock and on, we can keep discussing the midterm if you want to. And we can also do that tomorrow. So the wave function which we assumed is the wave function for particle in the box. So the computational entity is actually us confining particles to move in either a volume V if it's a three-dimensional system, it has volume L cubed. If it's a two-dimensional one, it has L squared. So basically the same type of problem is the one which we use. And then you have the spin part of the wave function. We use periodic boundary conditions, which give us a quantized wave numbers. The total Hamiltonian here contains, if we look at only the electronic degrees of freedom, because there is an additional piece here which comes from the background, the electrons interacting with a continuous smeared out background of ions, plus an interaction between the ions, which we have left out here, but we are bringing that back to life a little bit later. The kinetic energy is given by this quantity here, where these are the single particle energies for kinetic energy. And with these plane waves, actually these plane waves which you have here, they are eigenstates of the kinetic energy operator, which is normally not the case. In most cases, your single particle basis is not an eigenbasis of the kinetic energy. It's normally the eigenbasis of the kinetic energy plus some confining potential. That's normally the starting point. So the total Hamiltonian then, and these are things which we looked at last week. So we end up with a Hamiltonian which looks like this with spin degrees of freedom. And where we now are summing over the different so-called wave numbers, and these are states which we fill up to the Fermi level when we also are looking at the expectation value of the ground state. But in this case here, these K values, they represent different single particle states. And now I'm actually setting this up in terms of the wave numbers, and then we sum over spins. So these numbers are discretized, but then when we insert the plane waves here, when we look at these matrix elements, then we have some constraints which we discussed last week. So in this case, we just changed the integration variables and could rewrite this integral in terms of this specific integral which you see here. So this is just a quick reminder of what we went through on the whiteboard last week. And then I just brought this into the notes here so that you have everything here for completeness. Then you can use the properties of the Kronecker deltas defined in terms of these exponentials. And then you can show that this matrix element, as we've been calling them, which is just an integral over two particle degrees of freedom, then what we have then is that we must have a conservation of momenta. So we need to satisfy this restriction here. Then that means that we can then, with that restriction, we can rewrite this sum here and the sum of the spins in terms of this equation here, where we now got rid of one of the momenta due to momentum conservation. And then what we did was simply to define new variables, which means then that we could then calculate the expectation value of the reference energy. So we could calculate the kinetic energy, and this is a quantity we went through the derivation last time. And the kinetic energy, since this is a Fermi gas at 0 temperature, there is no Fermi-Dirac function for finite temperature, which means that we are now summing simply up over all the single particle states up to the Fermi level, and that translates in the infinite limit into an integral here. And then this is something which we then could rewrite in terms of the Fermi level. And we also found that the density of states is something which we now can rewrite. So the density of states is simply a way in the momentum space is given by this quantity here, where we have a factor of 2 due to the degeneracies in spins. So the homogeneous electron gas is a system with an equal amount of spin up and spin down electrons. So sometimes you may be interested in looking at polarized systems, which means that there is a specific spin degree of freedom, a final spin value. Now, when all the particles are filled with spin up and spin down, all the particle states, that means that the total spin sums to 0. And in our case, there is only one Slater determinant for the non-interacting system. Now, the thing which is nice with the plane waves and this type of systems, due to the translational invariance of the interaction, is that the plane waves are also eigenstates of the Hamiltonian, which consists of kinetic energies plus potential energy. So these are just quantities which we can calculate. And then that means that we can rewrite the energy now for the kinetic energy in terms of the density. And we have the number of particles which we now want to let go to infinity. But what we normally do then is that we calculate the energy per particle. So that means that the energy per particle is now given by a constant times the density to the power of 2/3. And this quantity rho, which you see, is nothing but n, which you have here, divided by v. That's the density as we defined it. Now, what we're going to do now is actually to look at this expectation value. And this is the quantity we are going to labor a little bit with now, because we have a specific expression for the matrix elements. Now, in this case, we have to be a little bit careful because the operator is now normalized with respect to a new vacuum. So there are going to be conditions on these matrix elements here. So we are going to spell out that in more detail on the whiteboard here. But the thing which is important here is that the only set of contractions which you can run, which result in non-zero results, are those which involve states below the Fermi level, by obvious reasons, because here you annihilate states below the Fermi level, and when you create a new state, it has to be below the Fermi level. And that puts some constraints on the type of values for the momenta which you can have. And then we are going to rewrite this one in terms of a specific term here. So let's now look at what this term here gives us. And then we are going to jump back and look at the calculation of this energy, where we also add the positive background and the positive charge contribution. And these are terms which will actually cancel parts of this integral here. So let's switch to the whiteboard. And after this reminder of what we did last week, just bring this up. Let me just find my proper notes here. So what we did last week, and that was the expression we ended up with, was to show that this interaction between the electrons, so the V interaction, and now we're not looking at the background part and the ion interaction, but this is just the part which comes from the electrons interacting with each other. So what we had was an expression where we now wrote it out in terms of a sum of a spin 1 and spin 2. And then we have a constant, and in many cases we often put these constants to 1, the natural constants like the charge, h bar, etc. And this is divided by 2 here. There was a sum over p and k and q. And we had an element which went like 4 pi divided by mu, which is a convergence factor, which we are going to drive to 0. And this contains an A creation operator of sigma 1 of k plus p. So this is a sigma 1, and this is a creation operator. And then we had another creation operator, which goes like A dagger. And then we had a sigma 2 here, and then a k minus q. So I'm putting vectors here to indicate that these are momenta with 3 components, or wave numbers with 3 components. And then I have an annihilation operator of sigma 2 of k multiplied with A of sigma 1 of p. And if we write this as a terms of a diagram where we have the interaction vertex and the different labels, what we had originally was a K1 here and a K2, and then we had a K3 and a K4. And here I'm omitting the spin degrees of freedom. So I'm just leaving out spin. I'm just looking at the wave numbers. Now what we had was a conservation of momentum, which followed from the integrations, which we did last week. And that contains, that should be a K4. Then what we did was to define new variables, a K1, which was just given by K3 minus this Q. And then we defined a K2, which was now simply, this is K3, yeah. And then we had a K2, which we then defined in terms of a K minus Q. We defined K3 as P. So that means that the expression, so this should be a K3 minus Q, and this is K, just a moment, I think I just put it wrong here. Now this should be a K3 plus Q, and this is K minus Q, right? So this is, and then I define K4 to simply be given by this variable K. So K1 then becomes equal to P plus Q. And if you look back at the expression which we have put K1 here as P plus Q, and this follows from momentum conservation. And then we have K2, which would be this case here, which is now this one, which we have defined to be K minus Q. So what we've done now is simply to rewrite so I should actually say that Q is equal to this quantity which we have here. And that is the same as K1 minus K3. So this should I actually wrote wrongly. So this should be K3 minus Q, sorry. And this Q is simply equal to K1 minus K3, which is also equal to K2 due to momentum conservation minus K4. Okay, so these were the quantities which we introduced last time. And then with these quantities, we can then rewrite this sum here in terms of one piece where we put Q equal to 0. And then we have the terms with Q different from 0. So this is roughly where we ended last time. So we have a sum over Q different from 0. And then we sum with the P and Q, like that. And then we have a sum over the spins, sigma 1 and sigma 2 here. And sorry, this is K. I'm going to put the vector signs here. And that gives us a 4 pi. So that means that this term here, since Q now is different from 0, this term is never 0. And then I have an A of sigma 1 of P plus Q. And then I have A of sigma 2 dagger of K minus Q. And then I have an A of sigma 2 of K. I have to be careful with all these subscripts. And then I have a P here. And then I have plus. And then I have the term where I actually put Q equal to 0. So this sum runs only over P and K. And a sum over the spins, sigma 1, sigma 2. And then I have a 4 pi divided by mu squared times this constant here. No, not constant, but this creation and annihilation operators. Now the term, which you will also find in the lecture notes, which I'm not going to deal with now, is actually this final term, because this final term here, when we calculate the expectation value of that one, so the expectation value of this specific term, and we'll just write P of K of sigma 1, sigma 2, and then I just put the constants here. You can actually show that this one becomes equal to E squared times 4 pi, and then it's divided by 2 times the volume, and then divided by mu squared, and then I have an n squared minus n here. Now, in the limit where n and v go to infinity, and then I take the limit mu goes to 0, then these terms here cancel the term from the background interacting with the electrons and the background interaction with the ions. So that means that this term here is exactly cancelled by 2 terms which come from the electrons interacting with the background of the charged ions and the ion-ion interactions. And this is something which I put back in the Jupyter notebook, or the slides for this week. And I'm not going to do that calculation, but the one I'm going to focus on is actually this part here. And we are going to calculate the expectation value of that quantity, because that's the one which is involving a slightly more tricky integral. And that integral is actually, it's useful to have seen that. It's perhaps not the most exciting thing we are going to do, but sometimes it's actually useful to have seen how we calculate specific quantities. So let's go through the calculation of that one. And for those of you who may have taken a course in atomic physics, you may have seen similar tricks. But let's slowly go through it. So what we are going to do now is simply to calculate the vacuum to vacuum, or the reference state to reference state expectation value of that specific quantity. So let's now look at the expectation value over phi 0 and the interaction piece. So V of phi 0, where that interaction is the one we are going to look at. And let's now just write this in the general form, as you will also see in the midterm. So in the general form, without us having specified any quantum numbers, this is given by a sum over half, and then I'm summing over all the states below the Fermi level. And then I have this term Ij of V of Ij minus Ij of V Ji. Now, keep in mind now that we are operating with a normal ordered Hamiltonian with respect to the new vacuum, but we need to take a closer look at that specific operators which we have. So in the calculations, what we have now for the specific operator, we are going to have a sum over sigma 1, sigma 2. There's going to be a sum over p. So these wave numbers are now going to replace these more general labels I and j. And these wave numbers are now going to represent all the states up to the Fermi level. But where we now, instead of having a specific single particle wave functions, we have the plane waves. And since these momenta are discretized, and we have a three-dimensional box, that means that these numbers here, they are now running over all the possible wave numbers we can have with a given number of particles in a box, as we discussed in the previous week. So in our case, we have also Q different from 0. And then we have this term, just a constant, V divided by 2. And then we have a 4 pi of nu squared plus Q squared. But then we have the creation and annihilation operators. So let's look a little bit closer at these, because we have an A of sigma 1 dagger, and then we have a P plus Q, and then we have an A of sigma 2, and then we have a K minus Q here, and then I have an A of sigma 2 of K, and then an A of sigma 1 of P. So now what we are going to do, when you look at these specific terms, you see now we have a state I here, which is below the Fermi level. And that means that if I now look at this set of operators, what that means is, so this is state I, and this would also be state I. So what we have now for the integral which we are calculating, we are seeing now that this term here requires actually, so if I look at I, so on the bra side, what we have is P plus Q. So the spin is the same, so that's no problem. But on the ket side, what we have is that we require that I takes the value P, right? So if I look at this specific integral and I plug in the explicit quantum numbers, what you see now is that this is not possible because Q is different from 0. So this integral here is actually due to the orthogonality of the single particle states. This is actually not possible due to momentum conservation, because we actually sorted out this specific term. So you see now that here I have the quantum numbers I, which on the bra side are defined by P and Q, and sigma 1. So we have a sigma 1, and then we also have a sigma 1 here. But then on the ket side, since I have now this specific state here, then this is not possible due simply to momentum conservation, which we have here. However, if I now look at this term, when I now look at particle 1 here and particle 2 here, that specific term, so this is the direct term. So the direct term does not allow me, due to the conservation of momenta, it doesn't allow me to have a term which is different from 0. So this term here is simply equal to 0. So the next term, if we look at this minus ij of v of j of I, and then now I'm going to plug in the explicit quantum numbers. When I look at that one, this is now given by the creation operators as a P plus Q. This one now is given by K, and that is actually allowed because that is the way we have defined it. And this, and then I have a sigma 1 here. And in this specific case, I need to have sigma 1 equal to sigma 2. So they have to be the same. So the spins, so this will have a sigma 2 here because I'm interchanging the states. This is going to be my sigma 1. So there's going to be a restriction on delta sigma 1, sigma 2 here in order for this to be different from 0. Then, so here I can actually have P plus Q is equal to K. This is allowed due to momentum conservation. And then for the other states on this would be particle 2 then, when I look at the integrals which we have to evaluate. So in that specific case, what I end up with is a K minus Q, which has to be equal to, in this specific case, to P. And then you see that this one, this constraint here, obviously matches this constraint here. So if I do that, then this expectation value, which I'm going to have now, there is no contribution from the direct term due to momentum conservation. So the only term which contributes is this one. And then I'm going now to plug in the summations over the spins. I'm going to put in the different values. So what we will get then is the following. So I get that P has to be equal to K plus Q, which obviously means that Q is equal to P minus K. So I can plug that one into my expression. And then I can start looking at the integral, because what I want to do now is also to drive. So this P minus Q now is different from 0. So what I get now is that this phi 0, when I collect terms and plug in the, so this V interaction, which we started with, phi 0, this is going to be equal to, when I sum over the spin degrees of freedom, I get a factor of 2. There's going to be a factor of 2 pi of E squared divided by this volume. And then I have, so this first one here comes due to the spin degeneracy. And then I have now a sum over P and K. And where K is different from P. And I've also taken the limit of mu goes to 0. Because I don't need to deal with that one now, because K and P are different. So I get simply a term which now looks like P minus K squared. So if you go back to the equation which we had, since what I did now is to replace Q with P minus K. And then I can take the limit mu goes to 0, because Q is no longer a quantity which is 0. So that means that what I get then when I've taken all the, used all the restrictions on the values of P and Q and K, then I simply replaced Q with the P minus K, and then plug that one into the integral. And what we need to do now is to evaluate this term here. Because this term now is a term where we want to take the limit where the volume goes to infinity. So what we are doing then is simply to take the limit of V, and if I take one of these momenta or wave numbers, this is going to go over to 1 over 2 pi cubed, and then I have an integral over dp, where this is a volume element which contains dpx, dpy, and dpc. So that means that when I now look at my integral, what I get now for the ground state expectation value of this term, this is going to be given by minus 4 pi of E squared. I need an additional term V because I'm missing that one. I had just 1 over V. And this is a 2 pi to the power of 6. And then I have an integral from 0 up to the Fermi level, because these sum up to the Fermi level. And then I have a dp, and then I have a 0 up to the Fermi level of dk. And this is multiplied with this quantity here. And this is something which we can evaluate analytically. And that's the kind of intermezzo which I'm going to do now, so that you see how you can actually evaluate an integral like this one and get an analytical expression. This is often skipped in most textbooks. People just state the expression. And I always find that a little bit frustrating, because there are some mathematical tricks which are extremely useful to have seen, because often, or in many applications, especially with electromagnetic forces, you may encounter integrals of this type. So let's see now how we are going to evaluate that specific integral. So what we can do now, if we just single out this piece and we just leave in peace all the constants. So we have a dp, and let's just write it like this, since this is a three-dimensional integral now. So a dk, and then we have a d3k. And this is going to be given by, when we write out this term, I have a p squared, and then I have a plus k squared, minus 2 times k times p times cosine theta. Okay, this is just writing out the absolute value. And since we are squaring it, we are getting a quantity like that one. So what we can do now is also to define new variables. So we can define a new variable, which we call mu, which is the same as cosine theta. This is a mu here. And then we are going to introduce a further new variable, so we can actually simplify this integral. So let's just skip also the integration limits, and let's just write it out when we perform this new change. So we have a mu of cosine theta, and then I introduce a new variable, which I call for s, which is k divided by p. So that means I can rewrite that integral, d3p of d3k, and then I have 1 over p squared. So I'm just introducing this variable s, and then I have a 1 over 1 plus s squared minus 2 times s times mu. Now, there is a very important mathematical property of Legendre polynomials. I don't know if you've seen this before, but one thing which we can do now, so what we have to be careful with is that P is not equal to Q. So we have already defined that. So what we can look at now first is that P is larger than K, which means also that the S is less than 1. So let's look at that case. So when we make the integral, we have to take into account the case where P can be larger than K, or K can be larger than P. But they can never be the same. And this follows from momentum conservation. So there is a very important generating function. And you may have seen that when you studied polynomials like the Legendre polynomials. So I can actually write a quantity like this with a minus. So this is normally called a generating function. And this is given by a sum which goes to infinity, from L equals 0 to infinity, of S to the power of L, and multiplied with a Legendre polynomial, which takes as argument cosine theta. So mu is just cosine theta. Have you seen this before? So this is one of the ways by which you can express Legendre polynomials. So Legendre polynomials are very important polynomials. So they are the solutions of a famous differential equation. And the thing is that recognizing this function here is something which is going to be of immense use for us when we now want to evaluate this integral here, because what you see here is nothing but that quantity squared. So if we square that quantity, what we get then is 1 plus s squared minus 2 times s times mu, which is then simply going to be a double sum. which I just call L and lambda. And then I have S to the power of L plus lambda and PL of mu of P lambda of mu. So these are just two polynomials. And the thing which is nice with the Legendre polynomials is that they have an orthogonality property. So when I'm integrating and summing over this L and lambda, then I can use the orthogonality properties of these equations, of these functions. So I don't know if you've seen this when you're solving differential equations. There are some very special differential equations which appear in many solutions of physical systems, but also systems in mechanics and many other cases. So you have the Legendre equation, you have the Laguerre equation. These are some of the, you have the Hermite equations, which actually lead to the harmonic oscillator, etc., etc. So these are all famous polynomials which lead to a set of infinite solutions and where the polynomials form an orthogonal and normalized basis. So what I'm going to use now is this property here, and I'm going to plug it in. And when I perform the integration, I can use the orthogonality of the Legendre polynomials. So if I use that and I look at the integral, what I get now, and I'm looking at a specific case here. So we have a d3 p, and p is less than equal than kf. I have my integral over k, and I actually left out the integral over the, I just leave the integral over p unchanged till now. I have a constraint on p now on k. And then I'm writing out here a dk, k squared, spherical coordinates. There is no dependence on the angle phi, so I can integrate that up, and that gives me a factor of 2 pi. And then I integrate over cosine, which gives me an integral limit from -1 to +1. I have a d mu, and this is multiplied with, and now I have to be a little bit careful because I have to introduce these terms with k and p. So I have k over p over L plus lambda. And then I have 1 over p squared. And then I have my PL of mu. And I have my p lambda of mu. And then there is an additional term, which I just leave like this. I have an integral over p less than k, and the integral over k less or equal than kf. And I just put dots here to indicate that the expressions are the same. Now, what I can use now, and this is the benefit of what we have done, is that the Legendre polynomials in this domain, they are defined from mu -1 to +1. What I have now is that there is a magic orthogonality relation of p lambda of mu of d mu, which is simply equal to 2 over 2 of L plus N1 of delta L lambda. So if I do that, I will actually get 2 factors, but the technical calculation of these is essentially the same. So I'm going to get a factor from here, and I'm going to get a result from here, and they're basically going to be identical. So I just get to multiply what I have from here with a factor of 2. So if I do that, what we are going to get when I plug in everything, so that means that I'm going to get 4 pi of d3 p, and this is an integral up to kf, and I have the integral over k less than p of dk, and then I have a sum over L, and then I have a k divided by p of 2L plus 2. And this is now multiplied simply with 1 over 2L plus 1. So let me show you how we can calculate this one. Now, if you now look at what we have, the sum over the L's is independent of the integral over K. So I can just do that summation without thinking of the integrals. I have a K divided by P to the power of 2L plus 2. So I can perform the integration over K now, because this is going to be equal to an integral which looks like 8 times pi. And I have the factor of 2 here. So I should multiply this with a factor of 2, which comes from the other case where P is less than K. So I'm going to get now an integral which runs like this, P. So this just integrates up to Kf. And then I have an integral from 0 to P of dk. And then I have a sum over L. And then I have K divided by P of 2L plus 2 multiplied with 1 over 2L plus 1. That one is nothing but the following. So let me just try to wrap up this one, and then we will have a final piece which we will start with after the break. So I get an integral over d3 of P, and now I'm integrating up over P for K. So that is going to simply give me a factor of P here. And then you see now when I'm integrating over K, I get a factor of 2L plus 3, obviously, because I have to integrate here. So that gives me a 2L plus 3. So I get then a sum over L, and I have 1 divided by 2L plus 1 and 2L plus 3. And now I'm soon there. So let's just wrap this up, and then after the break, so let me just sneak in 1 more minute. I hope you can forgive me for that, because I can integrate over P. So that gives me simply a factor of 1 divided by 4, when I actually have a factor of 8 pi squared. So when I perform the integral here, this gives me a factor of 2 pi from the angle, and I get another 4 pi from the angle. But then I need one of these factors of 4 pi in front of the integration over dp of P, because I have a P squared here and P, so I get a P cubed. And when I integrate that one up, I get a 1 over 4. But then I get in the integral here, I get a 4 times pi over the angles. So that means that I'm left with 8 pi squared. So I get from the angles 4 pi. So I get a pi squared. And then I'm integrating also dp, p to the power of 3. So that p to the power of 3 picks up this factor 4. So I get then kf to the factor of to the power of 4. And then I have a sum over 1 over 2L plus 1 over 2L plus 3. And here comes a final trick. If you look at this equation here, the sum over L, it's 1 over 2L plus 1. I just wanted to finish this one, so I hope you can forgive me. We just take a little bit longer break. If you look at this one, I can rewrite it in terms of 1 over 2, and I have a sum over L, and I have 1 divided by 2L plus 1 minus 1 over 2L plus 3. This is just a simple rewrite of that expression. Now, if you now look at the summations here, I can actually rewrite this as a sum over 1/2 plus 1/2, and then I have a sum from L equals 0 to infinity of 1 divided by 2L plus 3, which is the first sum, minus 1 over 2L plus 3, which is the last one, which is untouched. Now I get magically 1/2. So that means that that integral, if we now wrap everything up here, that integral simplifies considerably. I think this is beautiful, actually. I love this thing. I'm sorry for digressing, but these are some of the things which, some of these tricks, when you see them, you just say, this is beautiful. I don't know if you agree, but I don't like to impose myself on people, but I think this is actually beautiful. Because then this integral, which looked pretty nasty, of 1 over p minus k here, is actually equal to 4 pi squared. I have a factor of 1/2, and then I have a kf to the power of 4. And when I collect everything, when I do that, this expectation value, phi 0, of the interaction, the electron-electron interaction of phi 0, is simply given by minus 16 pi squared, pi cubed actually, because I had another pi factor, e squared divided by, actually, let me just write the final expression. This is equal to minus e squared v kf to the power of 4 divided by 4 pi cubed. And after the break, we are going to rewrite that in simpler terms, in terms of the density. And that's where we will make the link with the so-called local density approximation, which is widely used in density functional theory. So I'm sorry for going over time. So we should take a good break of 15 minutes. Went 10 minutes over time here. But I just wanted to conclude this calculation because it's useful to have seen it. And it's this kind of trick where you use this type of polynomials. If you recognize, let's say, a part of the integrand which has a form like this one, then you can use Legendre polynomials. Sometimes you have the generating function for other types of polynomials. Each of these specific polynomials, they actually have what's called a generating function. So if you happen to have an integrand, which can be written in terms of these polynomials, then if you're lucky, you can actually find an analytical solution. So what we did before the break was to calculate that specific integral. And we can rewrite this term in terms of the density if we want to do that. And this is something which we are going to use when we look at what's normally called the density functional theory, which is the next topic. But we can now rewrite this if we bring back these expressions which we had for the density. So let me quickly remind you of some of these quantities we looked at. So we defined this density, n, is now given by the number of electrons divided by the volume. We also had introduced this radius of a sphere, which every electron occupies. So we define this volume for pi of Rs cubed divided by 3 is now given by the volume divided by the number of electrons. And this one is nothing but clearly 1 over n. We found last time that this Rs can then be written as a 3 divided by 4 pi of n to the power of 1/3. For a system where we have an equal number of spin up and spin down electrons, we found also last time, so let me quickly remind you of these terms, is that the kf cubed was given by 3 pi squared multiplied with the density of particles. And when we had these quantities, we could then manipulate the equation for the kinetic energy, and we can do the same thing here. So that means that the integral which you see here now, with these kind of intermediate steps, we can then rewrite this term here in terms of the density. So if we do that, you see now that we have a kf, which pops up here. So we can rewrite this term, which we put up. And let me just bring it back again. I'll put that note somewhere else here. Okay. So this term here, this one, is something which we then can rewrite as a phi zero of V interaction of phi zero, which is now given by the density. So we can actually rewrite it as an E times V divided by 4 pi cubed. And this is equal, this is multiplied with 3 of pi squared of n divided by V to the power of 4/3. And what you see in here is actually the density. So what we can do then, if we can also rewrite it in terms of these constants we had last time. So when we now plug in the values, this can be written out as a 0.16 Rydberg, which is 13.6 electron volts, times the Bohr radius divided by this Rs multiplied with the number of electrons. And that means that the total energy, the expectation value of the Hamiltonian here, when we have included the kinetic energy and subtracted the background terms, we get something which runs like 2.21 divided by this radius, which a single electron occupies of a sphere, to the power of 2 minus 0.916. And this is an expression which you will find in many, many textbooks in condensed matter physics. And this is multiplied with 13.6 electron volts, 1 Rydberg. So 1 Ry is equal to 13.6 electron volts. And this energy is surprisingly close to the experimental value. And it's actually much better than we get with just a Hartree approximation. But the binding normally is much lower than what you would see experimentally. But the thing is that what you see now is that the exchange term is the one which gives rise to a contribution which lowers the energy. And it's a delicate balance between the density, which is reflected in this quantity Rs. So A0 here is just the Bohr radius, which is a quantity which absorbs E squared, the mass of the electron, and h bar. So that's a constant defined in terms of natural constants and sets a natural length scale. So these quantities here actually show a kind of balance between the repulsive forces and the kinetic energy for the system. And the thing is that the direct term or the Hartree term which we had, it disappears because that cancels the background charge and the interaction between the electrons and the background in the limits, in what's normally called the thermodynamical limit. Now, what we have here is actually an interesting result because it tells us that this interaction piece, when we now look at what we have here, n divided by v, it seems that the interaction piece is a function of density to the power of 4/3. Now, the kinetic energy, as we found some time ago, is actually a function of the density to the power of 2/3. So this is something which now can motivate us to think of us setting up a function of the energy in terms of density, and then vary the density instead of varying the single particle wave functions. So let's briefly summarize and look at this step between mean field theory based on Hartree-Fock and density functional theory, which in principle gives an exact relation between the density and the ground state with a given Hamiltonian. But at the end, we have to make approximations. But in principle, it's an exact theory because it deals with the one body density and the density of the system which is in principle the solution of a many-particle problem. So what we are going to look at now is the transition from density functional theory versus mean field theory based on the solution of the Hartree-Fock ansatz. So we can just say Hartree-Fock. So if we now look at Hartree-Fock theory, what we had is that the energy of the system is a functional of a single Slater determinant. Of an ansatz which we have made for the ground state of the system. And this ansatz is something which we call phi zero. And we would typically write this energy. This is the total energy. It's not the Hartree-Fock energy for the single particle states, because what we found then when we use variational calculus is that we found a recipe for finding this Hartree-Fock energy in terms of a set of coupled single particle equations. So in principle, what we did with variational calculus was to vary this wave function, and the wave function was varied so that we had a function which contained some admixtures, which we call a delta phi zero. And this delta phi zero was obtained starting with a Slater determinant and varying the single particle wave functions. So what we did was to assume that this phi zero is given by a Slater determinant. So we have I up to n, the number of particles, and then we have the creation. So I'm setting this up in second quantization now. So what happens is that we now could show, when using Fowler's theorem, that this term here in second quantization was the same as us making a small admixture of one particle, one hole excitations. So what we found then is that this delta, or what we postulated when we did the variational calculations, is that this was given by a sum over particle states and hole states, and we varied the coefficients for AI dagger AI acting on this state phi zero. So we could do this calculation in second quantization or in the standard configuration space representation, which sloppily is called first quantization. So essentially what we did is that we ended up varying the single particle wave functions. So in this ordinary configuration space configuration space representation, what we did then is that we had a single particle state of R, and we're leaving out the spin degrees of freedom. This was now replaced by a phi of I, which is a state below the Fermi level, plus some admixture, where we now included a state above the Fermi level. When we did that, what we found was a set of equations where the one particle, one hole, this transition probability is equal to 0. This followed from variational calculus, where we looked at a small variation of this energy, which is a function of phi 0, with respect to this delta phi 0 here. So actually, we just would write it like a delta phi here. And we required that that one had to be equal to 0. And what we ended up with then was a practical recipe where we found that these transition matrix elements or integrals of I of H0 of A plus the sum over all states below the Fermi level of I, of V, of A, of J, anti-symmetrized, had to be equal to 0. And that gave us a practical recipe where we defined a single particle Hamiltonian, which is given by this operator F. And we simply call that the Hartree-Fock operator. Now, the whole thing now is that what we have done in Hartree-Fock theory is that we started with a given Slater determinant, which we assume is a good representation of the answer of the ground state. And then we varied the single particle wave function. Using variational calculus, we then found this expression here, which then led to a recipe where we now solve a set of coupled single particle equations. And that led to us having defined an operator F, which is now the same as the Hartree-Fock operator. And when this acts on a basis, P, and this can be states above or below the Fermi level, this corresponds to this eigenvalue problem here. And the new basis is an eigenbasis of that specific operator. So what we're going to do now is actually to change this to a functional. So with DFT, density functional theory, we are now going to set up a functional of the density. So that means that we are going to look at the functional of the density of the system, which we also have labeled as an E of n. So I'm going to use n here. And we are now going to make a variation of the energy with respect to the density, instead of actually now varying the single particle equations. So we are going to find a functional, which we will define later more precisely. And we want to vary this quantity here with respect to the density. And this one is equal to 0. So that's the variational calculus. So we're going to use the variational calculus as before, but we are now going to vary the density, which in principle is given by the exact wave function for the ground state. So that's a different thing, because solving the many-body problem means that in order to find the ground state, so the Hartree-Fock is an approximation, where instead of solving the full many-body problem, we have now found a set of coupled differential integral equations, which look like a single particle set of equations. And they can be solved numerically with not too much pain. However, the total density is something which depends on the wave function for the ground state. And to obtain the wave function for the ground state means that we have to solve a problem which has time in 3 dimensions times n, the number of particles, degrees of freedom. And that's, in principle, a very difficult problem to solve by itself. So configuration interaction theory is one of the ways of solving this. So we are going now to define a Hamiltonian, which is given in terms of the density. And the attractive piece of density functional theory is something which will become evident, that the fact that one equation for the density is then remarkably simpler than the full many-body equation that involves 3n degrees of freedom for n particles. It is, however, in a certain sense too simple, because some of the approximations actually miss important physics, and that has to be baked in. So when Hohenberg and Kohn formulated the density functional theory, they were actually basing this on previous experience, where one of the previous functionals was actually given by something which is called the Thomas Fermi and Dirac functional, where the Thomas Fermi part is actually kinetic energy plus the external potential plus the Hartree integral. But then Dirac added the exchange part from the homogeneous electron gas. And that gave us a functional of the energy, which depends on density. So let's look at that as an intermediate step before we set up the Hohenberg-Kohn theorems. And there are two theorems with two corollaries, which we will discuss in more detail tomorrow. And these two theorems are extremely simple to prove, and they form the basis for density functional theory. But these two theorems don't give you a calculational recipe, unfortunately. So when we do the calculational recipe, then we have to actually plug in some kind of approximation. And that approximation, which we will discuss, leads to a set of equations which are almost Hartree-Fock lookalikes, and they're called the Kohn-Sham equations. This is something which we will discuss a little bit more tomorrow. Now, density functional theory is extremely popular, as I said in the beginning. It's widely used in material science. You can bake in a lot about the specific material you're looking at, whether you have a material in condensed matter physics, which can be set up using ions placed in different lattice sites. You can plug in periodic boundary conditions. You can plug in properties of that specific material, and then get a kind of mean field, which is supposedly is going to be more realistic than what you would get with a Hartree-Fock equation. And the calculational recipe is actually not that different from what you do in Hartree-Fock theory, but you keep adding physics information which is not included in the Hartree-Fock calculation. So let's just take a quick look at this Thomas Fermi approach, which was introduced back in 1927 by Thomas and Fermi. And then Dirac changed it by adding this exchange piece. So if you now look at the energy, the way we have set it up, so let's go back to a Hamiltonian now, which only contains the kinetic energy and the external potential and an interaction between the electrons. And we just leave out the rest. In many, many cases, you will see that people add the rest as well, which could be the interaction between the ions, the interaction between electrons and ions, etc. They are often thought to just give a constant background to the term which is most important for the correlations, which is the one which involves the interaction between the electrons. But you can replace electrons with other types of fermions. So density functional theory is widely used also in nuclear physics. It's widely used in other fields of physics, like quantum chemistry. There's tons of research. It's not only confined to material science and condensed matter physics. But let's now go back to the Hamiltonian, which we have set up. So this contains now a sum over the kinetic energy. And we have a minus h bar divided by 2 times mass. And now we're assuming that we have the same type of particles. These could be electrons. And then we have the kinetic energy operator. We have an external potential, I equal 1 up to n. So this is a potential which confines the motion of the particles. So this could be the field which is set up by the atomic nucleus. Or it could be some electric field which is set up to trap electrons. So this is something which we label as the external potential. And I'm just assuming that this depends only on the spatial degrees of freedom. And finally, we have a plus 1/2, and we have a sum over I and j, and where I is different from j. And then we have some interaction, which I just label as a v of the difference, as a function of the difference between I and j. And this Rij is now simply the relative distance and its absolute value. Now, there is another quantity which we calculated and introduced in the beginning of the semester. And if this is normally called the one-body density. Let me quickly remind you of these quantities here. And this is something which when we looked at this in the configuration interaction or the coordinate space representation, we would have a state R, a single particle state, and then we have a spin sigma, and then we have a position R prime and a spin prime. And this is defined, since we are assuming that there is no spin dependence, this is now defined as a product of psi I complex conjugate multiplied with psi I with an Ri prime. So this is an Ri here. Sorry, R. Let me just rewrite it so I get a little bit more space here. It got a little bit squeezed in. So I'm summing over all the particle degrees of freedom, and this is given by a psi of I and psi of I of R prime. Actually, that quantity is something which is calculated from, so this quantity here actually defines a one-body density, which we have discussed earlier in the semester here. So we would typically write this out in terms of, if I look at the diagonal part, this is something which we would get if we assume just one Slater determinant. Because in principle, the quantity which you see here is actually calculated from a specific expectation value. So we are going to rewrite this one in terms of an N of R. This is a typical notation which I'm going to use now instead of rho. Sometimes you will see this label as a rho, or you will find it labeled as an N. But this N of R is actually an expectation value. So if I look at that one, this is an expectation value between the state you have. So in general, this is the general expression. And you would typically assume that this could be the ground state of the system, but just let's leave it like this. It has to be normalized. This is a quantum mechanical expectation value. And this quantity, this operator of R, which we are evaluating, is now given by the sum over all the particles which we have. And then I have a delta of R minus R of I, which means that this quantity here is actually, that means that this N of R is actually proportional with an integral. So what we are doing now is that we are integrating out all the other particles. And that's why it's called a one-body density. So we integrate away all the other particles, and we just, this N, this R here, you could think of that as R1, but it doesn't matter whether you do look at this at R2, R3, and so on. And this is an integral over d of R up to N. And now, since we are having this Kronecker delta, this simply means that this is multiplied with this wave function, with this R fixed, and then I have an R2, an R3, and all the way up to Rn squared. And then it's divided by this normalization constant. If the state has been normalized, this psi, then this is just 1. Now, the thing is that the expression which I showed you earlier, this expression which you see here, this is based on a Slater determinant with a single particle basis. This function which you see here, on the other hand, can be the exact solution to the for the Hamiltonian to the ground state. So just keep it, this is what you see here is the general definition of a one-body density. This quantity here simplifies this N of R if you have a plain Slater determinant. And in one of the exercises in the very beginning of the semester, we actually calculated this quantity here with a single Slater determinant. So if you do a Hartree-Fock calculation, in the Hartree-Fock calculation, this quantity will simply be the sum over all the single particle states which define the Slater determinant for the ground state. However, if you have a more complicated solution to the problem, then you would need to perform this integral. So if you have somebody gives you the exact solution, this defines the one body density, where you integrate out all the other degrees of freedom. And this represents simply the probability of finding one particle in a specific position. When I now integrate up this N over R, there is actually a normalization condition here. So if I integrate up over all of space, N over R, this has to give me the number of particles. So that's a constraint which we will put on that density operator. So it's called a one-body densities because we're just integrating out all the other degrees of freedom. And it tells us what is the likelihood of finding a one particle in that specific position. And if I then integrate up over all of space, then that should simply integrate up to the total number of particles which are present. So that was a small digression about the density operator, the one-body density. And the thing is that these equations have been used in defining an energy functional. So one of the simplest one is now based on what we had for the electron gas. So this is called the Thomas Fermi Dirac functional. And this is roughly where we will stop today. And this one, E, as a function of density, we put a T, FD, Thomas Fermi Dirac, is then given by a constant. And this is the kinetic energy term. And then I have a D of R. And the kinetic energy, if we go back to the electron gas, had a kinetic energy term which depended on the density to the power of 5/3. So this is the kinetic energy, and this C1 is the kinetic energy constants which follow from the electron gas. So if you now use a one-body density, this follows from a one-body density calculation. That means also that the next term, which is the one which comes from the external potential, we have an external potential, Ex of R. If you remember the expectation value of that one, this is a one-body operator which acts at one particle at a time. So that means that in here, what we would have would be psi of R, complex conjugate, and in here we would have psi of R. And since this E of X as an external potential does not change the wave function, that means that we could actually rewrite this one as the wave function squared, which again is nothing but this quantity here. So that's just the density. Then we have the Hartree-Fock term, or the Hartree term. So the Hartree term has just the wave function squared. So that would be given by a integral over d of r. And then I have an integral over d of r prime. And then I have the density of one of the particles multiplied with one of the other particle divided by r. So this is a Coulomb interaction case. This is the interaction I'm having. So this is what we called the Hartree term. And you would get this one from the direct term in the calculation of the ground state energy with a reference Slater determinant. So this will be this term here, it just translated into coordinate space, the same as the sum over 1/2 ij of ij Vij of the direct term, just that specific integral. This is just nothing but that one, rewritten in terms of integrals as functions of the density. So here we are assuming that this density, n of r, is just given by this sum over all the particles up to the Fermi level of psi of I, the single particle wave functions squared. So here we've made an approximation to the one-body density. So what Kohn and Sham did, on the other hand, was simply to assume that there is such a function like this one, given in terms of the exact wave function. We are coming back to that tomorrow. But this approach here also includes a new term, which is the exchange term from the electron gas. And that depends also on the density. So it has an integral, but then it had the density to the power of 4/3. So this is normally called the local density approximation, but this is just the exchange from the electron gas. And this is the classical Thomas Fermi. So Fermi and Thomas did not have this term here. This was a term which Dirac added based on calculations of an infinite medium like the homogeneous electron gas. And you saw from the equation for the energy that we had a term which depended on the density to the power of 4/3. And the kinetic energy had, on the other hand, a term which depended on the density to the power of 5/3. So this is an approximation which is now made for the energy as a function of the density, but where the density is given by a single Slater determinant. This obviously is something which is an approximation, and for many, many cases where you have finite systems, where you have specific effects like finite number of electrons, you have shell effects, as they're called in atomic physics, molecular physics. You have electrons in a lattice, for instance, in condensed matter physics. This clearly is a very rough picture. And this is where density functional theory has its strength, because you can keep adding additional features into this term, which you see here. So a lot of density functional theory deals with us trying to bake in more and more complicated many-body correlations into that part. And that is an art by itself. So we are just going to limit ourselves to derive the Kohn-Sham equations, but we are not going to work more with density functional theory. But we want to use that one as, a way to exemplify how you can produce this higher order correction here from other types of many-body methods. So tomorrow we will discuss the central theorems in density functional theory. And although we took a long, long detour with the electron gas, to just get this term here, this serves as a starting point for the discussion of density functional theory, where you take the results from an infinite system and try to use that one for a finite system, which has obviously finite size effects. And that's where the physics is, the boundary conditions. So for those of you doing physics-informed neural networks, the physics is in the boundary condition. Okay, guys, I'm going to stop here.